recording, only because I'm scared I'm gonna run out of time here, which I did this morning, so it doesn't bode well. All right. So I do want to do some review just from last week. I saw that a lot of you have tried the assignment, so that's awesome. Just to kind of poke around in there, I'm happy to see that. But let's just do a little bit of review because, well, one, it's nice, but we're also, two, we're going to use all these concepts again today. Okay. So nothing really changes except for how we get our information changes today. That's it. Okay. And we do have quiz number 4. It's not until next Friday, right? So not this Friday, but next Friday. And I think it's the last one that I gave you kind of a buffer day, so we don't have material going up to it. We finish the material on the Tuesday before. Okay, so that'll be a nice change. So hopefully that is good. Just some review on the one sample mean t-test. Because like I said, we're going to use all of this stuff again. I kept forgetting the conditions, so I'm going to start with the conditions. I always forget the conditions. Because the conditions stay the same for the paired data that we're going to introduce today. Okay? And so the conditions, the first one is always independence. Right? What we've landed on is, as long as I've randomly sampled, I am allowed to assume that my observations are independent. Even if they're not, then I have to argue that these observations are independent of each other. So I'll say, if the sample was randomly selected instead of, otherwise I'm saying sampled. If the sample was randomly selected, we can assume the observations are independent. We can assume the observations are independent. The second condition is the normality condition. Remember, for mean questions, it depends on your sample size. And so I'll say normality. We decided to use, and it's pretty common to use 30 as our kind of baseline here. So if n is less than 30, so if we have a small sample size, then the distribution has to be approximately normal, or at least symmetric with no outliers. Okay, and so if n is less than 30, then the sample distribution must be approximately normal. Right. I'll follow it up with or symmetric with no outliers. If the sample size is greater than or equal to 30, then we can relax this condition quite a bit. We can handle some non-normality. We can handle some outliers, no extreme outliers, although if we have a big enough sample, so let's say over 100, we can even handle some of those extreme outliers. So it's sample size dependent, but here, as soon as we hit 30, we're saying good enough for government work. If n is greater than or equal to 30, we can assume normality. As long as there are no clear outliers. All right, let's just, as long as there are no clear outliers. Okay. We can handle some outliers, but just nothing drastic. We're going to recycle these conditions, so that's why they're worth mentioning. We're also going to do a confidence interval. So what was the confidence interval for the one sample mean? A confidence interval for the one sample mean, what we landed on was x bar plus minus t star with n minus 1 degrees of freedom times s over root n. This t star comes from that probability calculator that I showed you with the t distribution. All this other information came from the question. You have the sample mean, you have the sample standard deviation, you have the sample size, right? So there's a little bit more information that we're given in these problems. Right? Oh yeah, I was gonna say, maybe I'll say student distribution, just so we're used to seeing that in probability calculator. You could use the table, but I want to move away from the tables. I want you to start using that probability calculator, which you'll have baked into the assignments and the quizzes and the final exam. So if you know how to use it, then I'm happy. Okay. These values, x bar, s, and n, these are all given in the question. Okay. Just so we keep track of that. So it's just the t star that we need to know how to find, and it's no different than the z star. It's just now it depends on your sample size through your degrees of freedom. In terms of your hypothesis test, step 1 is to state your null and alternative hypothesis. So many colon on colon here. All right. Step 1, state the hypotheses. Hypotheses. The null hypothesis for a one sample mean question, we said was going to be, okay, is mu equal to some mu, not some hypothesized mu? All right. And then our alternative, as a default, we're going to use not equal to mu naught. Mu is not equal to mu naught, but depending on what the question is, of course, you'd have to change that sign. For step 2, do the test, which is calculate the test statistic. Yeah. So a test statistic is a generic term for a z, a t, the chi-squared, later on the f, all kinds of, it's an umbrella term that sees how far the sample is from the hypothesized thing generically. But yeah, so t is the test statistic, We said X bar, how far is it from mu naught? Hello? X bar, how far is it from mu naught? Taking into account the standard error, which for one sample mean is going to be S over root n, right? And so, and I like to do brackets just so you don't forget that that's one number, right? Once you have your test statistic, right? How far is my sample mean from my hypothesized mean? Then I can find the p-value. Find the p-value. We're going to use the probability calculator again. So we need our degrees of freedom is going to be n minus 1. And then use the probability calculator to find the p-value. And man, I wish I had just wish I was a little bit taller. Wish I was taller. All right, let me just, I'm gonna make myself one more line here. Well, I did in my head. I think I only know the first couple of lines. I wish I was a little bit taller. I wish I was a baller. I wish I had a girl. If I did, I would call her. I wish I had a rabbit in a hat. I think so. And something and an impala. I don't know. Whatever. I'll look up the lyrics. I'll be better next time. All right. Don't get distracted, Emily. Okay, here we go. The p-value depends on, the alternative hypothesis, right? So let's remind ourselves the three options. Uh-oh. All these different distributions, it's okay. I want to keep it on this one line so bad. The alternative hypothesis, if the alternative hypothesis is that mu is not equal to mu naught, then my p-value is going to be the area in both the tails, right? We need to know which area we want, because otherwise I can't put it into that probability calculator. It does all the work for me, but it can't read the question for us. If the alternative is that mu is less than mu naught, that's going to be the area in the lower tail. And if the alternative is that mu is greater than mu naught, that's going to be the area in the upper tail. Oh, I wish I could. It's like there's no space here. Conclusion is the same, right? Same as always is what I was going to write. We'll have an example where we will do an example or a conclusion rather. So, all right. Fine, I'll put it on this page. Step 4. Wait, how do I redo? I undid too far. Step 4 is the conclusion, which is the same as always. That's why it's so worthwhile. How you state your conclusion is always going to be the same. You're going to compare your p-value to the alpha level. Then that will determine what your conclusion in terms of H naught is. And then you can use that to state your conclusion in terms of the question, right? That's always your conclusion. I'm not going to write that down here because we're going to do a proper one. So it's worth memorizing that. And then one day it'll just come to you naturally. Okay, but before that happens, memorize it, right? Memorize the two ways that things can happen, right? Either the p-value is less than the alpha level, which means you have enough evidence to reject H naught, or the p-value is not less than the alpha level, which means you do not have enough evidence to reject H naught. Those are your only options, right? So memorize those until eventually one day it will click, I promise. So like I said, today, we're gonna recycle all that stuff that we learned last week. Okay? And the only thing that's changing is that now we're gonna talk about paired data. I might slip up and call it matched pairs. So I just need you to be aware of that. They're the same. Okay. It must be from when I learned about this stuff. We called it matched pairs, and I'm finding it really hard to shake. But you can see that they mean the same thing. Okay. What is paired data? All of a sudden, what's going to happen is we're going to have two samples, right? We saw that coming. We saw that for proportions, right? I have one sample proportion. I want to compare it to a number. Oh, what if I have two samples, each with a proportion? How can I compare these? It's not surprising, okay? But so now we have two samples. However, what's special about these two samples is that the observations are paired, right? You've got sample 1 and sample 2 have paired observations. Okay? Usual examples are things like pre and post scores, right? And so if I run a tutoring service, I get you to write some sort of entry test to see where you're at, right? Give you a grade. And then I administer tutoring to you over some amount of time. And then I get you to write an equivalent test, probably not the same one, that would be weird because you've already done it once, but an equivalent test. And then I can look at the difference in the scores, right? And so that would be paired data. So it's whenever we have two observations on the same subject. Okay. I had to take a run at it here. So in paired data, we're going to have two samples. Okay. In paired data, we will have two samples. But I'm going to say often because it's not always the case, and that's just me being picky, right? But often the observations in each sample, right, are going to be, I have repeated measures, but seems a little wordy, fine. But often the observations in each sample will be paired, but I'm going to say will be repeated measures on the same subject. And like I said, a common example is kind of a pre-post treatment analysis, right? Treatment is generic, right? It can be the tutoring that I administered. It could be a medical treatment, of course. It could be just time, right? It could be a lot of things. So treatment is very generic. Okay. But some before and after scores are typically what we're dealing with. Okay. I'm going to summarize this because this is quite wordy. Okay. And It's whenever we have two measurements on the same subject. Right? That's going to be paired data. Two measurements on the same subject is going to be paired data. All right, that's the type of question that you have. I do want to kind of clarify, same, there are scenarios where they're not exactly the same. You might be using twins or you might be using siblings, right? In terms of the measurements, they're similar enough subjects, right? You're starting from the same point. Okay, so it gets a little bit boggy. In fact, the question that we have is not an example of what I was talking about, so forget about it. I just realized that's not true. It is the same subject, and usually it is going to be the same subject, right? But there is some flexibility, right? So here, I'll say same or very similar. And it depends on what you're measuring too, right? For example, siblings or spouses. Right. I'm going to bring in the little blurb from the textbook as well, just because it's nice to have. These are all definitions of the same thing, right? Why is it so important that we're able to recognize paired data? So two sets of observations are paired if each observation in one set has a special correspondence or connection with exactly one observation in the other data set, right? Pre, post, that kind of thing. Okay. Why is it so important that we're able to recognize these? Because when you're reading the question on quiz 4, dun, 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 right? You need to be able to identify, okay, is this data paired? And I'm going to give you some clues just to kind of say, okay, yeah, I think it's paired, right? I think this is a paired data question, right? Let's just confirm. But what's going to happen is we are, of course, going to have two samples and they're either paired or they're independent samples, right? And we're going to treat how we analyze those is going to be different, right? So we have to be able to identify, okay, I've got two samples. So far, we only have paired data. On Thursday, we're going to have two independent samples that we need to analyze. Okay, so we need to be able to figure out what type of question we have. So just intuitively, right? Let's say, I like to use a running example, like I do a running clinic, but let's do the tutoring one that I started with, right? So I start a tutoring business and I want to prove that I'm able to improve people's scores with my tutoring, right? Seems reasonable enough, right? And so I have that same setup. I take on a new client, I guess, weird. And then I have them write the test, see where they're at, right? And then we do some tutoring, I don't know, a couple of weeks maybe. And then I have them write the test again. I have a pre-score and I have a post-score. Okay? But to summarize that change, right, I would calculate the difference, right? What's the difference in the pre and the post scores? And that's going to summarize what happened after with my tutoring, right? And so, and then I would be able to do that for each of my students. Now, if you think about it this way, right, I might have a student who's coming in for tutoring, but they're already a very strong student, right? Their pre-scores are going to be quite high, right? But if I'm doing my job right, then their post scores should be higher, right? And so, but then I have another student who comes in and they're not as strong, right? So they wouldn't write quite as well on that pre-test, right? But they would still be improving in the post-test. Really selling my own tutoring business. Everyone's improving, right? But we capture that in the differences. Okay? So what are we going to end up with? We end up with one sample of differences, right? But then all of a sudden I'm back to a one sample mean situation, which is what we spent last week talking about. And so then we're back in familiar territory, right? So it's just one little tweak and we're analyzing the differences. So what I'm going to say is to capture, I'm trying so hard not to say differences, to capture a change. To capture a change from the pre-scores to the post-scores, just generically, from the pre-scores to the post-scores, we calculate the difference for each observation. We calculate the difference for each observation. And then analyze the one sample of differences. And then analyze the one sample of differences, which is basically taking us back to a one sample mean type of question, right? Basically back to a one sample mean type of question, which uses those formulas and the conditions that we reviewed at the beginning of the class. So just to illustrate how this goes, I want to use an old trusty example that I've had that I stole from some textbook billions of years ago here. I just think it's a funny example. Well, maybe it's not that funny, but Jocko's Garage. Well, maybe I'll put it on its own page here. Okay. Jocko's Garage, here we go. Insurance adjusters are concerned about the high estimates they're receiving from Jocko's Garage. Sounds fishy, right? To see if the estimates are unreasonably high, each of 10 damaged cars was taken to Jocko's and a trusted garage, and the estimates were recorded. Is there evidence that Jocko's estimates are significantly higher than the estimates from the trusted garage? Okay. So now, right, we have two samples here. We have a sample of estimates from Jocko's Garage, and we have a sample of estimates from the trusted garage, but we're also looking at estimates of car number one, but twice, right? So I have these two observations on the same subject, right? The same car. So here I have two samples that are paired. So right away, I know that this is going to be a paired data type of question. Yeah. And maybe what I'll do is I'll just bump this down. Give myself a little bit more space here. Whee! How do I? Okay, looks like I'm gonna rewrite this. That's okay. Oh my gosh. Undo. That are paired. Only because I know I'm gonna have to copy and paste later anyways. All right. So here we go. Car number 1, compared to just kind of cruising through these values, doesn't seem to have a ton of damage, right? So Jocko's estimate is $500, and then they took the same car to the trusted garage and they quoted $430, right? Jocko's estimate was higher, right? But what we want to know is, okay, are Jocko's estimates just consistently significantly higher than this trusted garage, right? So what we're going to do to capture that, okay, car number 1 didn't have a ton of damage, right? We're going to look at the difference in the estimates, right? Whereas car number 2 seems to have quite a bit of damage, right? But if we look at the difference, right, then we can analyze just the differences in the estimates. Okay? So here, what we're going to do, and of course, you will never have to calculate the differences. That's insane. That's not where we're at anymore. Okay. But I do want you to see it happening, just so that you can kind of understand that, okay, I need to analyze the difference, or the differences rather. It's important, and nay, really important, that you do your subtraction in the same order, right? Because a positive has to mean something and a negative has to mean something. So if you're kind of doing it willy-nilly, then it won't work. So up here, I'm going to say my difference, I'm going to calculate Jocko minus the trusted garage. It doesn't matter as long as you're consistent. For me, my brain won't work if I do the right hand minus the left hand, but I can't. Okay. Now I have these differences, so let's just jot these down. 50, only because there's one coming up here with -50, right? A negative means that the trusted garage's estimate was $50 higher than Jocko's estimate, right? Which is kind of evidence against this idea of his estimates being higher, right? But let's see here. 20, again, -30, 130, 90, 160, 150, and 210. Once I have these differences, you can pretty well just ignore all the rest of this information. Okay? We're now boiling it down to one sample of the differences. And I'm going to give you the mean and the standard deviation. Of course, you could use some online calculator or R or something to find these, but it's going to be, the mean is 80 and the standard deviation is 84.59052. Okay. One thing that's really important to note here, because of how means work, they will subtract to be 80, but that's because it's linear, I guess. Yeah. And whereas the standard deviation has a square root, and so we can't just subtract them, right? So what I want you to note here is that 550 minus 521 is not 84, right? And so just keep that in mind. So if you don't have these values, you do need to calculate the standard deviation of the differences. Okay. It's kind of a common mistake that I see is is even though I give you the standard deviation of the differences, people tend to want to just take the subtraction. It doesn't make sense. Right? But just be aware that that happens. Remember, for a one sample mean problem, I need to know the mean, I need to know the standard deviation, and I need to know the sample size, right? We have all that now, right? 80 is the mean of the differences. So usually to highlight that it's for the differences, I do a little subscript diff. Yeah. The standard deviation of the differences, right? So S diff. I remember when I first was learning about pair data or matched pairs, I could not wrap my head around the sample size. For some reason, I can't explain it now, because it's the sample size of the differences, right? But I think I was always hung up on, well, I had 20 observations, so what? But remember, we're boiling it down to just the differences. So the sample size of the differences is 10. Okay. So we're going to have that same information. It's just about the differences, but really that's the only change. Okay. I like to, so of course, like I said, maybe on an assignment, I'll get you to calculate the differences just to emphasize that, okay, you need to analyze the differences, find the mean and the standard deviation of the differences. But in terms of a quiz, I would never make you do that. I would give you all this information. So one way to quickly recognize a paired samples question is if you're given information about the differences, right? The mean and the standard deviation of the differences. I will often also give you information about the two original samples. That's not a decoy. It would just be weird to not give all the information about all the samples, but as well as the differences. So usually, if you have something that's laid out like this at the bottom here, then that's a clue that it's a paired data type of question, right? Then you can read the question and just confirm, right? Just kind of, okay, reassure yourself that it is a paired data question. And then we're off to the races. So here, I think I said it, but I didn't write it down. So once we've calculated the differences, in fact, once we have the mean and the standard deviation of the differences, that's all we need, well, and the sample size, right? And then we can ignore the rest of this information because we've caught everything that happened. Calculated the differences. Once we have calculated the differences, we can ignore the original two samples and analyze the one sample of differences. We can ignore the original two samples and analyze the one sample of differences. Must have been half asleep this morning when I did. Let's start with the conditions for paired data. So this was just to kind of have something to talk about. Okay, we're going to work through this example but I want to kind of give you the rules of the road in general for paired data. Yeah. And so let's start with the conditions. Conditions for paired data. Just as a side note, these are the same as one sample mean. First condition is independence. But Emily, they're paired. How can they be independent? Well, the subjects have to be independent, right? Because we're talking about the differences. And so the subjects were randomly selected. Then we can assume they're independent of the other subjects, right? So not, the pre and the post scores, those are not independent. In fact, they're paired, which I guess is a condition. But here I'm going to say the subjects, and I'll highlight that for a brief moment. As I went to highlight, I thought I should make sure that ink is dry. Oh, that's weird. Subjects were randomly selected. When you highlight ink that hasn't quite dried yet, it makes a mess. But that was a weird blast from the past. Subjects were randomly selected. The normality condition, n less than 30. The distribution of differences needs to be approximately normal. Distribution of differences needs to be approximately normal if n is greater than or equal to 30. As long as there are no extreme outliers, then we're good to go. And I'm going to show you one way that you can deal with that with this example. So those are our conditions that we're going to check, right? Same as before, nothing changed. In terms of a confidence interval, it's going to be the same formula that we had before, and we can apply the same interpretation as long as we're interpreting the differences, the mean of the differences. Okay. And so for our confidence interval, we said, and I'm going to give a little bit of space because, spoiler alert, I'm going to put a little subscript diff on everything that's from the sample, and that's the only thing that changes. So x bar plus minus t star times s over root n. So I'm going to add a little diff here. Our degrees of freedom is still n minus 1, but because it's the number of differences, it's the n diff minus 1. Oh, made it look like the minus is on the diff, minus 1 there. The standard deviation of the differences, the n of the differences. Really no change except where the information is coming from. So here I'm going to say same as last week, right? When we worked through one sample means, we spent some time developing the t distribution, but that's all we did. But it takes some time. So same as last week, except we're now analyzing the mean difference. We are now analyzing the mean difference. words matter, right? Because on Thursday, we're going to analyze the difference in the means. So notice how that's not the same as the mean difference. The mean difference is the average of the differences, and the difference in the means is the difference in two separate means. So it's going to get kind of boggy, right? But just remember, words matter, and just be patient with yourself. Okay. So in terms of our hypothesis tests, what's really nice is once you've decided that this is a paired data type of question, right? Don't look back. Then you've decided that that's how you're going to analyze this thing. Okay. Your null hypothesis will always be the same. Cha-ching. So step one, to state the hypotheses. Your null hypothesis will always be that mu diff equals 0, right? In the one sample mean case, it was mu equals mu naught, okay? But remember, in our hypothesis testing, we have to assume that now the two samples are the same, which means the difference is 0, right? And so I always have to assume that the mean of the differences is 0 until I have proof otherwise. So we're always going to compare it to 0.
Can't be greater than the last time.
It can be, but not in this course. You got me. You got me. And it's pretty rare still. I mean, in theory, you could do anything you wanted, but in practice, I'm ready to commit. This will always be the null hypothesis for paired data. This will always be the H naught for paired data. The alternative hypotheses, so it's kind of a give and take, because, okay, so we have this fixed null hypothesis, but the alternative makes us work a little bit. Okay, so we're gonna have three options again. Mu diff is not equal to 0. That one's fine. However, once we get to mu diff less than 0 or mu diff greater than 0, that sign depends on how you found the difference, right? So if I did Jocko's minus trusted and I want to show that Jocko's estimates are higher than the trusted, that means my difference would be greater than 0. However, if I had done the trusted garage minus Jocko's, if Jocko's estimates are higher than the trusted garage, then I would have less than 0. So you see how it would depend on how I calculated the differences. So here, these signs depend on how you calculated the differences. Depend on how you calculated the differences. For example, we did the difference is going to be Jocko's minus the trusted. And we wanted to know, and I always find it's helpful if I just kind of jot it down and just kind of look at it, right? Is this, we want to know if this is higher, right? Which means that Jocko's minus trusted would be greater than 0. So then my alternative hypothesis is that mu diff is greater than 0. One way that you can confirm that you got that right, because that's it's a little sticky, right? And so one way that you can confirm that that makes sense, it's easy. If you're doing a two-sided test, not equal to, I just want to know, is the difference significantly different from 0? Ugh, wording. But in this case, if I want to know if Jocko's estimates are higher, right, does that mean the difference is greater than 0? For a one-sided test, positive 80, I can only use positive 80 to prove that it's significantly greater than 0, right? I can't use positive 80 to prove that it's significantly less than 0, right? 80 is more than 0. Is it significantly more than 0? Taking into account the spread, right? And so that's one way that you can kind of check in. Okay, do I have a positive number? Then that's all I can prove, right? Step 2, do the test. We calculate the t again. And again, I'm going to leave a little bit of space to put on little subscript diffs just to highlight that they're all diffs, but nothing else is changed. Technically minus mu naught over S over root N. So what I'm going to have here, X bar diff, S diff, N diff, nothing else changes. Except mu naught, we said, is always going to be 0 for us, right? As soon as I have paired data, then this is always 0. Mu naught equals 0 for paired data. Since H naught is that mu diff equals 0. Oh. How far is the mean difference? So the sample mean difference from 0, is it significantly far enough away from 0 to reject the null hypothesis? Step 3. So we're not going to do this quite yet. I want to go through the steps just to show you that there's nothing really new here, and then we'll do the hypothesis test for this question. Find the p-value, which means we need the degrees of freedom, which again is going to be n diff minus 1. Oops. Then use the probability calculator, right, to find the appropriate p-value. And then just to keep it on the same page, I feel like I'm constantly stressing about these page breaks. Step 4 is your conclusion, which is the same as always. I'm going to nab this blurb and just the summary information here. Hello. Okay. And this is all the information that I need. Just choose the wrong option. It's X bar. So this is the typical layout or kind of the information that we need for paired data. So if you had to read this, so you're sitting in the quiz or the final exam and you're reading this and you're like, oh, I think it's paired. I don't know, does she give me the mean of the differences and the standard deviation of the differences? I did. Wow, that's so nice of me. Right here, this was Jocko. This was the trusted, and this was the differences. Yeah. Okay. Whenever you want to answer, is there evidence? It's really asking, do a hypothesis test, or I guess that's what it's saying. So this means do a hypothesis test. Oh, and I guess we need the sample size and diff is 10. Okay. Let's check our conditions first. And if we read this, right, to see if the estimates are unreasonably high, each of 10 damaged cars was taken to Jocko's. So there's no mention of randomly selecting these 10 cars. So I just want to show you how to deal with that because we can. We're really just assuming that all these cars are independent of each other. In fact, we're assuming the damage on each of the cars is independent of the other cars, which is reasonable and opens it up to my, I like to seal the deal. And I usually like to start saying, it's reasonable to assume that, because no one can argue with that. So our conditions, the first one is independence. There's no mention of randomly sampling the cars. So what do we say? We say, or I like to say, it is reasonable to assume, like I said, that really no one can argue with that unless it's actually unreasonable. It's reasonable to assume the damage on each of the cars is independent of the other cars, right? I'm saying that's a reasonable assumption to make, right? If you disagree, then fine, right? But that's an assumption that I'm making and I'm going for it. So it's reasonable to assume the damage on each of the cars is independent of the other cars. Because we're talking about the subjects, right? Or each of the cars is independent of the other cars. I can only think of a few kind of absurd situations where that wouldn't be reasonable to assume, right? But yeah. There's like a monster truck rally situation in my head where they're all just going for it. That would be weird. So I feel safe with my assumption. The normality condition. I think the easiest way would be to make a histogram and just make sure, does it look approximately normal, right? So we could make a histogram. I don't want to do that, and that's fine. I'll show you another way that we could do it. Okay. So here, we could make a histogram of the differences to check for normality. And with these small sample sizes, we're really just looking for symmetry with no outliers / symmetry with no outliers. Okay. But instead, what I'm gonna do, because I don't feel like doing that, okay, and I want you to have another tool that you can use, is I'm gonna look at the most extreme difference, right? The most extreme value. Okay. So the largest difference is, let's go back there. So remember, I'm focusing on just the differences. The largest difference, positive or negative, is this 210, right? So what I really am concerned about is whether this is an outlier or not. What can I do? I can standardize it, right? I can see how far is 210 from 80 if the standard deviation is 84.59. If it's within, 2.5 standard deviations, I'm safe, right? Even 3, we could push it to 3 if we're desperate. Okay, but I'm gonna check that 210. If 210 checks out, then I can assume all the other ones are within, normal range. So the largest difference is 210. We can standardize this value to see if it would be considered an outlier. If it would be considered an outlier. Right, 210 minus 80, how far is it from the mean, taking into account the standard deviation? I'm going to do 84.59, and I get 1.5368, da da da. Okay. This is not a concern to me. 1.5 standard deviations away from the mean, that's not considered an outlier, right? You could even use something like the 1.5 IQR rule if you wanted to get really nitty gritty, but that involves finding the mean, finding the quartiles, doing the 1.5 IQR rule to see if there's outliers. That's another way that you could do it. I'm just trying to save a little bit of time, right? Here, if I just pick out the largest value, see if it's an outlier, which it's not, then I think I'm safe.
Considering over 3 an outlier?
Yeah, 2.5, 3. It's kind of, well, it depends on how desperate you are to do the analysis.
On the exam? No.
Yeah.
I'll just say it's about
And therefore the conditions are not satisfied. The rest is blank. I'm like, what? It's not wrong, but kind of you have to play along. Yeah, it depends on how desperate you are to please your client. Yeah, 4 standard deviations away. Yeah, it's fine. Yeah. No, that's how you get more money. Oh, well, if we increase our sample size, right, we'll just redo the study. I'm confident that we'll satisfy this normality condition.
Say the conditions aren't met.
Yeah, I'm like, it does. Well, yeah, then I'm like, I'm stumped. It does kind of irk me when someone says the conditions are not satisfied and then they just do it anyways. It's like, that's the opposite of what I wanted you to do. But yeah, I do want you to do the questions, even if they get weird like this one. But so what did I wanted to summarize what we did here. So since the most extreme difference since the most extreme difference is approximately 1.5 standard deviations from the mean, standard deviations from the mean, I'm going to say I'm not concerned about outliers in this data. I am not concerned about outliers in this data. You could end there, but I'm just going to kind of summarize that. Therefore, we can assume the normality condition is satisfied. We can assume the normality condition is satisfied. If you have a large enough sample size, right, then we would argue, okay, well, the t-distribution is quite robust, we say, to outliers. So even if there are some, it can handle it as long as our sample size is large enough, right? So then if the sample size was 50, for example, for the normality condition, I would just say, well, with a sample size of 50, the t-distribution is robust to outliers and the normality condition is satisfied, right? So you just kind of leverage that sample size. But in this case, we only had 10, so then we need to do a little bit more digging, right? Over 30, floodgates are open. All right. Step 1 for this hypothesis test. Now we already did the work for finding our null and alternative hypothesis, so I'm just going to steal that here, but we're going to state the hypotheses. The null hypothesis, once I've established that this is a paired data question, is going to be mu diff is equal to 0. And right, we had to do a little bit of groundwork, but our alternative hypothesis was that mu diff is greater than 0. And I'll just make a note here that this was done earlier. Oops. You know what? Oh. Step 2, do the test or calculate the test statistic. T is the mean of the differences minus 0, which you don't have to write. I just want to emphasize that we're still doing that same calculation, divided by S diff divided by the square root of n diff. Now I've already got it here, so it's 80 minus 0, 84.59052 divided by the square root of 10, and put that in brackets. Common mistake here is everyone's so concerned with the degrees of freedom that all of a sudden you're doing n-1 in here, but it's just n, right? And so that would change your answer just ever so slightly, and it would probably be marked wrong. But I would look at it afterwards. So T is going to be 80 divided by 26.749871117, which gets me to a T of 2.9906686609. You can round that let's do T is approximately 2.991. Right, to 3 decimal places. Now, what I'm finding is the probability calculator inside the assignments are showing up fine. It's just when I go to the raw link, it doesn't show me the bottom. So I'm just, but I do want to maybe screw that up. Hopefully not. Okay, so here's where, wait. Come on. Here's what it looks like. Okay, when as a default, with the T distribution, we have to change it to the student T distribution. We have to change the degrees of freedom. Now I know I have 9 degrees of freedom. I guess I didn't write down that I was about to do the step 3. I'll write it before I. Fine. I got ahead of myself. Step 3. Find the p-value. The degrees of freedom is n diff minus 1, which is 10 minus 1, which is 9. 3 lines. I was saying this morning, my nephew's going through a phase where he says, I'll never do that. But he says it with like such gusto. He's like, I'm never doing that. I'm never gonna cut my hair. I'll never write across the page, is what I'm thinking of. I always stack my equal signs, and it hurts if I can't stack my equal signs. So I'll never write across the page. Never, ever. All right, so I already did the 9 degrees of freedom. This is where we need to check back on our alternative hypothesis. Remember, our alternative hypothesis was that the mean difference is greater than 0, which means I need the upper tail, which we changed here, right? Wait, there. And the value that I want to put in there, the value I want to find the area in the tail for is going to be positive. Oh, it doesn't want to. Okay, 2 point. What the? Hello? Do you guys see that little cursor? It's on the move. Oh boy. Okay. It's always something. Why is it doing that? Is there a clear on here? GeoGebra. Okay, well, this is a weird glitch, and if you do find this, let me know when you're working in it. It was fine this morning, so I'm gonna steal the screenshot from there. How about that? How about them apples? If I can figure out which one. Is it this one? Yeah. Okay, I only used 2 decimal places. I was feeling lazy this morning, I guess. Okay, just as a note here. I just used T of 2.99. That was weird of me, but that's what happened. Your 9 degrees of freedom goes in here. Just remember that you have a one-sided test, and in fact, you need the upper tail, and then the p-value is this one here. Right, so then the one-sided p-value is 0.0076. And just as a reminder, we use this one since the alternative is that mu diff is greater than 0, right? I know that connection takes a long time to build up to, right? So I just want to emphasize it every time, okay? That connection between the alternative hypothesis and which tail area you need. Now that we have a p-value, we're ready to finally state our conclusion. All right, so step 4. And I'm gonna do it this time. It's the conclusion. First thing we do is compare the p-value to the alpha level. Since the one-sided p-value of 0.0076, notice how I'm constantly showing off all the things that I have under control, right? I'm showing off that I know it's a one-sided p-value. I say what the p-value is, okay? And it is less than the alpha level, less than the assumed alpha level. Assumed because I'm not going to scroll back up there, but there was no alpha level that was given, so that's fine. Assumed alpha level of 0.05. We have enough evidence to reject H naught. We have enough evidence to reject H naught. If I'm going to reject it, I should say in favor of what? In favor of HA. Which means what? In terms of the question, it means we have evidence to say that Jocko's estimates are significantly higher than the trusted garage. Therefore, we have evidence that Jocko's estimates are significantly higher than the trusted garage. Significantly higher than the trusted garage. Three parts, right? Compare the p-value to the alpha level. Hello. What does that mean in terms of the null hypothesis? Remember, we did all our testing assuming the null hypothesis was true. Until now, we have evidence against that. So your conclusion in terms of H naught. And then finally, the one people love to forget, your conclusion in terms of the question, arguably the most important. Now, I know I'm out of time. So that you have it. But the hypothesis test told us that Jocko's estimates were significantly higher, but it didn't tell us how much higher, right? And so that's where we would need to do a confidence interval, right? So as a default, let's build a 95% confidence interval, right? So a confidence interval will tell us how much higher his estimates are. Turns out, blah, 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 you can work through it, blah, 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 blah. It's between 1949 and 140 and 51 cents higher, right? And so, and then I also had grand ideas, but I think that's good. I'll parking lot that example. If you have any questions, let me know. Otherwise, I'll see you on Thursday.
With the GeoCubra calculator,
Yes.
mine was only giving me a lower bound. I don't know if it might just be